To me, engineers were the most important people in the world. In those days, Hewlett-Packard only made test equipment for engineers, analog engineers. And I was engineer building equipment for engineers, so I wanted to be rated that way. And I passed out my schematics so people would see how great it was, and that they could build their own computer for $300 if they knew how to build things.
Obvious answer is, let's build bigger atoms, right? Okay, that's Silicon Valley thinking. And guess what? That's actually what we do. But what we do is we make artificial atoms where you still get the physics of quantum mechanics, but it's with technology you know how to build. In a classical system, you can either have 0 or 1 as your logical state, either of those. And in quantum physics, it can be both at the same time. It means you can kind of do a parallel processes where you can take some logical operations, you can run 0, you can run 1, or you can run 0 and 1 at the same time, and it forms a parallel processor. I've been working on this technology personally, and this is a very nice photo. You can see the chip in the center, and then there's a bunch of wire bonds to a microwave compatible circuit board, and then a bunch of microwave connectors on the outside where we're going to put in the microwave tones and do the manipulation of the state. And this is kind of for a test device. We have bigger ones to do our bigger chips. This is a chip that we have in the fridge right now with about 30 lines or so. The aluminum is where the chip is housed in a shielded box. And then all these things go to various filtering, because if we have any noise coming down to our device, it will kind of mess up the quantum calculation. It's very fragile. And then all this hardware is put in what's called a dilution refrigerator that's operated at about 10 millikelvin, 100th of a Kelvin. Remember, room temperature is 300 Kelvin, because you have to get rid of all the thermal noise in order to see the quantum effects. The progress in our group is very rapid, and we hope to be showing some really interesting, kind of useful, powerful, potentially useful results very soon.
And this is something that's fairly new. This is the last 24 months, that we are able to have these long, non-linear functions represented in data structures that are learned, that remembers that 50 steps back, that was a good move. It led to the big win up here. That depth of understanding, that's new, and that's what's game-changing to the world we live in. What I want to show you is how you can teach computers to do things without programming them. So if someone ever told you that a computer can only do what it's programmed to do, they were wrong. The blue block is trying to move around, and it gets a negative point every time you hit the red one, and it gets a positive reward, +1, when it hits the green one. That's all we told it. And then every time it moves, it cost it 1/10 of a negative point. So moving a lot cost you, hitting the red one cost you, and hitting the green one is a reward. Look after, 10 minutes of training, what happens? It figures out how to generally not touch the red one and always chasing the green one. It's just 10 minutes of training. So yes, I could write this algorithm in C. I could fairly quickly write this algorithm where I, the all-knowing programmer, knows how to chase the green one and not hit the red one. I could also just take a generic reinforcement learning algorithm and let it learn it.
computing ecosystems are also starting to change in some pretty dramatic ways.
My experience at TechIgnite made me aware of so many opportunities.
And I would do all the steps. I would think out what I could do with what chips. I'd start looking through manuals. I'd start drawing little things on paper by hand.
As a developer, it's a privilege and a responsibility. It's a privilege because we're changing the world, and it's a responsibility because we're changing the world.